So from our last time, this is our definition for linearly dependent, and then linearly independent is not dependent. So and the question is, can we find values, constants that we can multiply each of these functions by and set them equal to 0 to see if we get non-zero constants? Uh-oh. My pen doesn't work anymore. Oh, there it goes. So we have C1 times 5 plus C2 times cosine squared x plus C3 times sine squared x equals 0. So we can do this by inspection or whatever, see if we can find C1, C2, and C3 not all 0 so that this would work. Yeah? Yeah, so we got this cosine and sine business, so if we make C2 and C3 to be the same, we can make them equal to 1, or we can make it equal to 5 or negative 5 or whatever. So there's a bunch of combinations you could take, yeah? This is for differential equations.
This is also part of them.
Yes.
So C1 were negative 1, C2 was 5.
Yeah, so if you let C1 be negative 1 and C2 and C3 both be equal to 5, then this would be non-zero solutions. So let's see, negative 1 times 5 plus 5 factored out with a cosine squared x plus sine squared x. This will give us negative 5 plus 5, which is going to be 0. So this works out. So what does that mean? What can you say about these things? They are linearly independent or dependent? Dependent. If you can get this to be non-zero values to make this equal to 0, then it would be dependent. If you let C1, C2, C3 all equal to 0, then that's of course going to equal to 0, and so that's not much to talk about. But if you can find any other numbers aside from 0 that would make this disappear, then it would be dependent. Now, if the only way you can get this to equal to 0 would be if C1, C2, and C3 are all equal to 0, then we would say they're independent. Yeah? Well, somebody just noticed that there's a sine squared and cosine squared. So if these two numbers over here were the same, you can factor that out, and then that'll be 1. That'll be constant, and then this is a constant. So they just came up with numbers. Right. Yeah. So the difficult part about this is that they may or may not be a set algorithm that would work every time for this. So if we're talking about vectors, if we were in linear algebra and we're talking about vectors, then we can change these equations and make them look like matrices and stuff like that, and then we can easily find them. But they're functions, and so it's a little bit more difficult to find an algorithm for this.
Can't you just pick a value for x?
No, it has to work for all x's.
So even if you pick the value for x, it would help out?
No, it wouldn't. Yeah. So this has to work for all x's. So now that I did mention a matrix, that's where we're going here. To find a more set algorithm for this, somebody came up with a method And we saw this at the very end of last class, called the Wronskian, a method where you take the determinant of a matrix, and hopefully we don't have to deal with determinants that are bigger than 3 by 3s, because finding determinants isn't that easy either. So we'll talk about finding the determinant of a Wronskian matrix. Well, first we'll define a Wronskian, then find the determinant of that. And this theorem gives us the criteria for linear independence. So if we lay out the functions f1 through fn, and then we take its derivatives and keep them in these rows, and then we find the determinant of this matrix, then that expression is going to give us a value, a function. And it says here y1 through yn are solutions to homogeneous linear differential equations on some interval. Then the set is linearly independent if the Wronskian is not equal to 0. So let's test it out with something that is dependent. So we should get 0 for our Wronskian. And and then let's get some practice on finding the determinant of the matrix. So let's use this same 3 functions over here and set up our Wronskian. So the Wronskian of 5 cosine squared x and sine squared x. Yeah, w in parentheses and however many functions you have is equal to, this is a matrix, but we're taking the determinant of this matrix, so we usually just use a vertical bar to say that we're going to take the determinant of that. And we'll list the functions. First, we'll list them out in order up on top. So this is 5. I'm going to make some space here because when I take the derivative, it looks like I might need some stuff. Cosine squared x and sine squared x. The derivative of 5 is 0. That's nice. The derivative of cosine squared x is 2 cosine x to the first power times sine x, or negative sine x. Negative. And derivative of sine squared x is 2 sine x cosine x. The derivative of 0 is 0 again, and then the derivative of this looks like it might be a product rule. So let's see, derivative of the first, that's 2 sine x times the second, sine x plus the first, negative 2 cosine x times the derivative of the second, positive cosine x. So let me rewrite that as 2, and then I'll factor out a 2. This looks like it's a sine squared x minus cosine squared x. Did I get the negatives right? Okay. All right, so not much simplifying there. There's some trig identities that we combine this, but let's not worry about that too much. All right, the derivative of the second one is derivative of the first is 2 cosine x times the second, cosine x plus the first, 2 sine x times the derivative of the second minus sine x. So let's see, 2 factored out. Got a cosine squared x minus sine squared x. So that's my Wronskian. To find the determinant of a matrix, you guys know how to find the determinant of a matrix? Go off on a little side note here. The objective was to get the determinant of this. If it's 0, exactly 0, then it is dependent. If it's not 0, then it's independent. So the determinant of A, B, C, D, E, well, let's see. Determinant of a 2 by 2 matrix A, B, C, D is going to be the product of the diagonals, AD, subtract the product of the wings, BC. So your determinant of a matrix will end up being a number. Determinant of a 3 by 3 matrix, and let's use A, B, C, D, E, F, G, H, I as our matrix. It's going to be a bit of a process, and what we do here is we say we expand on a row or a column, and we can pick any row or any column we want to expand on. So let's say, just for simplicity's sake, we expand on the first row. And what we're going to come up here with is we're going to take A, and then after we select A, what we're going to do is we're going to cross out the row and column that A is in, and then we take the submatrix that's left, E, F, H, I, and take the 2 by 2 determinant of that. And then, so when I say we're expanding on a row, what we're going to do now is we're going to select B, I didn't put a sign on this yet because the sign alternates. So A is positive, B is going to be negative, so you're going to take the sign of B, cross out the row and column that B is in, and then multiply by the submatrix that's left, which is D, F, G, I. And then you do that to expand on the last one. You get this last number on that row, C, and this one is going to be a plus. So there's an alternating plus minus as you walk along a particular row or column. And then you take the submatrix after you cross the row and column where C is in, and then you have D, E, G, H, and you can figure out that 2 by 2 determinant. Okay? So if you're familiar with a cross product, this is one way to get the cross product, is through the determinant of the matrix, aside from trying to memorize some long formula. And if you were to find the determinant of a 4 by 4 matrix, you would essentially do the same thing, except you'll have intermediate steps where you're doing a 3 by 3 matrix at a time, and then when you do a 3 by 3 matrix, you expand on it, and then you do a 2 by 2 matrix. Okay? So we do have a choice of either expanding a row or a column, and depending on row and column, we could expand on any row or any column. Tyler? For this one, we expanded on row 1. So what would be an ideal situation to expand on in our example when we're trying to find the determinant of this? The first column has zeros. So it would be an ideal situation to expand on this because your other two terms here will have 0 times something and 0 times something else. Yeah?
So is the Wronskian the matrix or is the Wronskian the determinant of the matrix?
Wronskian is technically the determinant of the matrix.
Okay.
So the Wronskian of functions is defined to be the determinant of this thing.
I just feel like it looks weird because it looks like it's saying that it's the actual matrix.
Well, what they did is they technically and notationally, if you have a vertical bar for the
Oh.
matrix, then it's understood to be the determinant.
That's what you're saying.
Yeah. All right, so let's expand on the row, and because of these zeros, it'll make our work a lot easier. So the determinant will be equal to 5 times the determinant of the submatrix, which is minus 2 cosine x sine x, positive 2 sine x cosine x, 2 sine squared x minus cosine squared x, and 2 cosine squared x minus sine squared x. And then if we continue to expand, our second term here will be 0 times something, and I don't care what that something is anymore because I'm multiplying it by 0. And then plus 0 times something else that again would equal to 0. So we go back to finding a determinant of a 2 by 2 matrix, and so we have 5 times, and this looks like it's going to be, let's call it a minus 4, and I'll distribute. I think if I distribute, I will have a cosine cubed x sine x negative 4, negative is a positive. This 2 gets multiplied also. This would be 4 cosine x and sine cube x. So the diagonal, and then minus, so there's a minus sign while you're doing the determinant, and then the wings would be 4 sine cubed x times cosine x minus 4 sine x cosine cubed x. So if I did this correctly, hopefully, because we found that they were dependent, right, in the previous page. So if I look at this, this is a minus 4 cosine cubed sine x. That's 4. So this has a negative with this negative outside, so this is actually a positive, so that's gone. And then these two are exactly the same with a negative in between, so this is equal to 0. So through the Wronskian, we found that these things are linearly dependent. Okay? So a lot of times when the functions really look different from each other, You can probably eyeball it and just say, oh, they're linearly independent. But this is just a good way to check to make absolutely sure. Like sine and cosine by themselves are linearly independent, but if you square it, you notice now that, and then you throw a constant in there, you notice that it's not linearly independent anymore. So just have to be careful about special cases. Most of the time we'll see that these functions are independent. All right? Yes?
For linearly independent, do they always get constants or do they get functions as well?
If it's independent, non-zeros, you could possibly get functions. Yeah, so you don't just get, if this was linearly independent, then you might get something that's not, as long as it's not zero. Well, maybe we should do a quick example of functions that are linearly independent. I just want to do two functions. I don't want to do three. And I don't want to do an absolute value. Actually, let's do number 16. No, there's a 0 there. All right, let's just make one up. I think we showed last time that the sine and the cosine functions are linearly independent from each other. Let's actually see it with a Wronskian. So with the Wronskian, this is going to be a 2 by 2 matrix. We'll list the functions in the first row, sine x, cosine x. Oh, this is going to be a constant. The derivative of sine is cosine, and then negative sine. So the determinant of this is negative sine x squared minus cosine and cosine is cosine squared x, which is equal to negative 1. So these two are linearly independent. Okay, so to address Liz's question, if they're all going to be constants, let's do another one. X and e to the x. I'm pretty sure this is not going to be constant. Let's see what happens. So x and e to the x are the functions in the first row. The derivative is 1. The derivative of e to the x is e to the x. So the determinant is x e to the x minus e to the x. And this is not exactly 0. So these are linearly independent. Yeah?
And the derivatives of the functions, do they have to be alike, like all x's or all y's, or can they combine?
No, we're talking about just functions of x only, or t only. I hope not. Maybe in the homework, but I won't give you a quiz or a test question that has more than 3. Yeah?
If you get a function that find a value of x that makes that 0, it's still linearly independent.
Yeah, it's still linearly independent. I think 1, if x is equal to 1, that would make this thing equal to 0. But that's not a condition for this. This has to be 0 for all x. So, no, that just means it's probably not going to be in a domain of something. So this one says if your Wronskian is not equal to 0 for every x in there, then it's independent. So that means that this thing has an x is equal to 1 solution if this was set equal to 0, but you're not going to care about that. As a check for linear independence, we wanted to see if it was exactly 0. No, we don't say that either. All right, so that's the Wronskian. Any questions? So all this discussion was prompted or started by taking a look at higher order differential equations. And then we talked about higher order differential equations and coming up with solutions and a bunch of different solutions possibly. So we're still back to that idea. Let me put the differential equation again that we're dealing with. And you don't have to write all this stuff down again. So this is the differential equation that we've been dealing with. It's remember that we want it to be linear. It's a linear differential equation. It's a higher order differential equation because if it was a first order linear, then we'll just do integrating factors and we're done. So we're looking at order of 2 or more. And we're looking at this point at a homogeneous differential equation, and then we'll take a look at the non-homogeneous counterpart of that. So back, I'm looking at a theorem here. Where's my theorem? So if we have a differential equation, a homogeneous differential equation like this first one, and then we found, this is an nth order differential equation, so if we found n linearly independent solutions, we introduced a superposition principle last time where if we just take those n solutions and we multiply it by a constant and then add them all together, then we have another solution that's going to be our fundamental solution. Maybe I'll do a recall here. Y double prime plus y prime is equal to 0 was an example that we looked at of a differential equation. This is a homogeneous second order. Actually, I don't want the prime here. This is a second order linear differential equation, homogeneous. And then I said, well, we found one solution that worked. I think it was sine. Is it sine that worked? Sine x. And then we found another solution, which is cosine x. I don't know if e to the x would work. No, e to the x wouldn't work because it's... So this is our solution. These are two solutions that we have, and we just show that they were linearly independent, right? So according to this, we have a fundamental solution. Set to be a fundamental solution. Oh, these are called fundamental solutions. And then what I was mentioning, getting ahead of myself, was that the superposition principle says that if we take a linear combination of those two fundamental solutions, then we get a general solution. Okay. So we have fundamental solutions, and then we're going to string this together to make a general solution. Let's see. So the general solution of your differential equation would be the linear combination of those fundamental solutions. So if y1, y2, all the way up to yn are all solutions and they're linearly independent, then those are your collection of fundamental solutions. And if you put them together, then you get the general solution. Okay? If one of them is missing, then you don't have the general solution yet. So to get the general solution for a homogeneous differential equation, you need to have as many fundamental solutions as you do the order of the differential equation. So if it's a second order, we're looking for 2 fundamental solutions. If it's a third order, we're looking for 3 fundamental solutions. Okay? All right. So back to this example that I have over here. We have the differential equation, we have the 2 fundamental solutions, and so we can just complete that by saying the general solution is going to be the y. And usually when you have fundamental solutions, those individual functions, we call them y1, y2, y3, or whatever, and then if we want the general solution, we have the y without a subscript. And this is a linear combination of the fundamental solutions. So C1 times sine x plus C2 times cosine x. And like we've seen before, as many of the as high as the order is, we'll have that many constants, parameters. Okay, we still haven't figured out how to find them, but we're kind of theorizing stuff right now, and then when we start finding these things, we'll put it together and string all these things up. So these concepts are just to help us prepare so that when we start finding these solutions, we can string them up together and find our general solution. Okay. We have really been focused on the homogeneous differential equation. If your other side is not 0, then you have a different problem. But it's very close to what we've been doing here. So we just need to tack a little something on to find our solution. So, any questions about the homogeneous part? Okay, so I think we're done with the homogeneous differential equations. Let's take a look at non-homogeneous. So the non-homogeneous differential equation kind of builds on its homogeneous counterpart. With one more step or one more function to deal with or to find. So here's our first definition here. Any function yp that doesn't have any arbitrary constants is called a particular solution to a non-homogeneous differential equation. So if we have that, again, we're still dealing with higher order, but still linear. We're still dealing with linear differential equations. When we start going off into nonlinear differential equations, then that's a different story. So we're still dealing with linear differential equations of higher order, and if it's non-homogeneous now, then we need to find another solution that's called a particular solution. Now, the kind of tricky part is that when we think of particular solutions, we think of solutions with an initial value problem. But this isn't quite the case yet, because we're not necessarily dealing with initial value problems here. We're just saying that if we don't include any constants, this is free of arbitrary constants. If we have an actual function that would work for this differential equation, then that's called a particular solution. Okay, once we can find that particular solution, which we still don't know how to find, but once we can find that particular solution, then we can find the general solution for a non-homogeneous differential equation. Is it all getting kind of mushed up? Yeah. We really, I guess we just need to start finding these solutions. We're still, this is all theory behind it, so that when we start finding solutions, we can just put it all together. So maybe I'll just go a little quicker and all right, so a general solution for a non-homogeneous differential equation needs your fundamental solutions and a particular solution that would work for that non-homogeneous differential equation. And if you string up your fundamental solutions like you did before for the homogeneous part and tack on that particular solution, then you have the general solution for your non-homogeneous differential equation. So, yeah, you treat part of it like you're dealing with this is a general solution for a homogeneous, and then you just add on a particular solution, and then you have the general solution now. Notice that the particular solution doesn't have an arbitrary constant. This is an nth order differential equation, so we need n parameters and arbitrary constants, and that particular doesn't have an arbitrary constant.
So you could just set your equation equals 0.
Yeah, that's how you would solve for a non-homogeneous differential equation. Is first you have to solve for the homogeneous differential equation, and then you have to find a particular solution. Okay, so how you find a particular solution? Well, first, how do you solve for the homogeneous differential equation? And then, how do you find a particular solution? Once we start doing these things, then hopefully this will fly a little bit better. Victor? No. We would, if we were looking for solutions, then if we were looking for the fundamental set, then we would use a Wronskian to make sure that they're all linearly independent. Okay. So, what's this? Whoops. Superposition principle. Boy, we don't need to talk about that. There's a summary in the textbook that you can probably look at. I think I got this directly from the textbook. And it tells you basically what I just mentioned. If you're dealing with a homogeneous differential equation, you have the fundamental set. And if you're dealing with non-homogeneous differential equation, you have the same fundamental set from the homogeneous counterpart, and then you have a particular solution. Okay? So we'll talk about finding the particular solution a little bit later on. Let's start solving for some differential equations.
I'm confused about the reduction of order thing, because wasn't that sort of what we were calling when we were doing this substitution for f ax plus bx something?
No, when we were doing a substitution for the first order, all we're doing is we're shifting the variables from a y of x to a u of x or v of x or something. But the order is still the same.
Oh.
Okay, in this reduction of order, you're actually going to rewrite your differential equation from a higher order to one less higher order, one less higher order. All right. So still, the difficult part about this is that we have to assume that we have a solution already. We have one solution. And so what we have to do is, given one solution, can we find another solution? And we can do this by what's called reducing order. So if we have a second order differential equation and we have a solution that we know of, can we bring it down to a simpler differential equation that we can solve for? So the answer is hopefully yes. We can do a substitution and then try to solve for it. I think there were some examples in the book, in the section. Let's see if we can do one of these problems. Let's see. Let's pick two. So in our example here, we have a differential equation, and then we're assuming that we know a solution to one solution to this differential equation. Yeah, we just still don't know how they got this. How did they get this? I don't know. But let's just say we got this somehow. We got a solution, and let's see if we can find one more solution. This is one of the fundamental solutions. It's not a particular solution. Particular solution in the context that we're talking about would be a solution for a non-homogeneous differential equation. So let's just say this is one of, I'm looking for two fundamental solutions, right? Because this is a second order. So I'm looking for two fundamental solutions, and I'm given one of them already. So I just have to find the second fundamental solution. We should really check if this works. Let's just assume that it does. Okay, so our substitution is going to be y is equal to u times y1. So that is supposed to be our substitution. So performing the substitution for u by making another substitution. So what are we going to do here? Oh, did I just forget? I just forgot how to do this.
Oh my gosh.
What? You can solve. Oh, man. Blank. All right, let's see what we can do. So this is supposed to be a solution, so it should work. So let's try to find y prime of x. So this would be a product rule, I think, right? Derivative of the first times the second plus the first times the derivative of the second. And then take the second derivative, which is another big product. Derivative of the first times the second plus the first times the derivative of the second. Y prime, y1 prime. And then u prime y1 prime plus u y1 double prime. So I think that simplifies a little bit, right? U double prime plus u double prime y1 plus u prime y1 prime, and then there's two of them, plus u y1 double prime. All right, what a big mess. Let's see. So we got u double prime y1 plus 2 u prime y1 prime plus u y1 double prime plus 2 times u prime y1 plus u y1 prime plus u times y1 is equal to 0. Is that right? How to what? Well, that's the suggestion that they made, is that you let y equal to that, and then took the derivative, because if y is a solution, then if I put it in here, it should work out.
Oh, and then you just replace W, or you replace U prime with W.
Well, yeah, almost. But let's see. Let's continue working this out. Since now I got rid of the y's, I have y1, but I know what that is, and I can try to find out what that is, work that out, and all that stuff. But I have u as my new function that I'm solving for. So I'm going to collect all the u's together. So I'll take the u double prime times y1. That's a u double prime times y1 term. I'll collect all the u primes. That's it. So I have, how many of those do I have? I have, so there's 2 and 2, that's 4, right? 4 u prime y1. Oh. Oh, okay. So it's y1. So 2 y1 prime plus 2 y1. Is that right? And then u prime. And then And then so what's left? What's left is just the u, so that's a y1 double prime plus 2y1 prime plus y1, and that's multiplied with a u. Is that right? Now what? Yeah, did you guys catch that? This is y double prime plus 2y prime plus y, and it's y1 that's in there. So because y1 is a solution, when you put y1 into this differential equation, you would get 0. So this whole term goes to 0, and we actually lose this u, which is good, and that allows us to make the substitution that w is equal to u prime. Does that make sense? That's how you reduce it by order. So what we said in the beginning was that y1 is a solution. That means we didn't check this. I said maybe we should check, but we didn't. That means if you put y1 into this function, into this differential equation, that you should get this to equal to 0. So this is y double prime plus 2y prime plus y. So this thing here, this expression is actually putting y1 into this differential equation. So it's y1 double prime plus 2y1 prime plus y1. And so that is exactly 0. All right. We could probably do some more simplifying, but let's see if we can do the substitution now. We're going to make two substitutions. One of them is we're going to put the value for y1 in. So y1 is equal to this. We also, looks like we're going to need y prime. So it's derivative of the first times the second plus the first times the derivative of the second. So that's y prime, y1 prime. And then the other substitution that we're going to make is the u prime is going to be w. So that means u double prime is going to be w prime. So if we take the derivative of both sides, this becomes a double derivative, this becomes a single derivative. So those are the substitutions that we're going to make. And then it becomes a first order differential equation. So let's actually see that happen. We have a u double prime, which becomes a w prime. We have a y1, which is x e to the negative x. We have a 2 times y1 prime, which is e to the negative x minus x e to the negative x, plus 2 times y1 times u prime is w, is equal to 0. Say it again? This is correct. This is a process that you have to go through to solve for this. We could, after we do this, we might be able to find some shortcuts. We know that the u has to disappear for us to make that substitution, so we know that there's going to be this portion that's going to be gone. But there's going to be more stuff that can come up. Okay, what else can we get rid of? Between these two, we have two e to the negative x, and then we have a negative 2x e to the negative x, and then there's a positive 2x e to the negative x. So that would disappear, and then this becomes a little bit easier. We have x e to the negative x times w prime plus, and then we have 2 e to the negative x, and then these other two terms go away, and that's a w is equal to 0. And then if we divide out by e to the negative x, then that's not going to change anything. We just have x w prime plus 2w is equal to 0. So this is a first order linear equation that we can solve for, I think. It actually, I was going to say, is it separable? Yeah, I guess it could be. Bring the w over, divide by x, and then bring the w back, because this is 0, so that makes it nice. So anyways, we'll solve for this somehow. I'm going to do the integrating factor business. Oh, let's do the separable stuff. Let's see. X w prime is equal to negative 2w. Let's bring the w down here. Let's call this dw dx so that we can actually see the separating. So we can divide by x on both sides. dw dx is equal to negative 2w over x, and then just whatever you do, whatever it's called. So dw over w is equal to negative 2 dx over x. So integrate, we have the ln of w is equal to negative 2 ln x plus c. And then we probably want to take this 2 to a power e to the ln x to the negative 2 plus c. So this will give us an arbitrary constant. We can call it a or whatever. A times e to the ln of x squared, which is just the ln of x to the negative 2, x to the negative 2. Wow. So are we done? No, we're not done. Actually, the constants here, you know how the integrating factor, you found the constant? You can kind of throw away the constant here also. So anyways, we're not done yet, because this is just w, and remember that we're looking for y, and so in looking for y, we have to find u. So we have to go from w. We said that w is equal to u prime. Right? W is equal to u prime. So again, I'm going to ignore the arbitrary constant here. So w is equal to u prime, which is equal to x to the negative 2. So to find u, what do you need to do? So take the integral, and this would be negative 1 over x. All right. So are we done? No, because that's what u is equal to, and then I have to multiply that with y1. So to get the other solution, you need to take your u function that you just found, 1 over x, and then multiply that with y1. y1 was x e to the negative x. So this will become just e to the negative x, or negative. So there's our second fundamental solution. Actually, the negative sign, like this a constant over here that I just ignored, and like any other constant that might come up, we can just ignore that also. So our y2 of x would just be e to the negative x. So that means for this differential equation, the general solution is going to be given by y is equal to, what was it? X e to the negative x plus e to the negative x. And since it's a general solution, we'll throw in a, this is where we throw in a C1 and a C2. Wow. Because that constant, when we throw the arbitrary constant out here, it doesn't matter if it's positive or negative, or if we have any other constants next to this, it'll get absorbed by this because it's a constant. Yeah, so y2 I got this one, but since this is going to be part of a general solution, this is a fundamental solution, e to the negative x and negative e to the negative x are basically, they're linearly dependent. And so I would just vote for the simpler one between the two of them. If it had a 5 here, I still would get rid of this constant just so I can express it as a fundamental function, fundamental solution function. And then that would, that 5 or negative 1 would get absorbed by the constant anyways. So decide to ignore that. Whoa, that was fun.
So we do this when there is a second order differential equation?
You do this when there is a higher order differential equation. This would work best for the second order differential equation because it'll reduce it to a first order differential equation.
But only homogeneous.
Yeah,
Here.
only homogeneous at this point.
You have to give them one solution.
At this point, yes. Now, when I look at this differential equation, we can actually, there will be a process for us to find a solution to this differential equation without having to go through this big mess. But theoretically, they're setting up a stage for something that could possibly be a little bit more challenging or difficult. Like if we had a third order differential equation, we can use this process to trim it down to a second order, and then we can solve for it. Okay. So it's a lot to think about. I'll give you guys a quiz next time.